Okay, good afternoon, everybody. So let's start our lecture. This will be our fourth lecture, right? The second week.
You guys think he's going to be 10 minutes late to the online lecture too?
Today is August 26th,
Asking for a
right?
friend.
Okay, you can hear me. Can you hear me, everybody? Can you hear me? Can you hear me? Okay, so good. So let us start our lecture today, and today is August 26th, 2021. So this will be our fourth lecture, right? So if we go to D2L, first of all, that is our main hub. So I uploaded a quiz, that is quiz 0, syllabus and policy quizzes, policies. So I see that half of the people you have taken this quiz, so please complete it. Okay, this is an easy quiz. Most of the questions are related to my syllabus and our syllabus and policies. Okay, so then what else? Okay, so our syllabus is as is. We do not have any update or change in our syllabus. I think it is stable now. It's good. So let us go to the syllabus. This is the one. Okay, and let us go to our course schedule. So according to our course schedule, so this lecture today we will discuss master theorem mainly. So our goal will be to discuss master theorem. So in your book, if you go to what is the page number? In the actual book, if you go to page number 93 in PDF, so here you will give 115, maybe 105. Okay, then 114. So then you got the master theorem. Okay, so today our goal will be to understand master theorem and its use. How do we use it to solve some problems? Okay, so master theorem is a mathematical, is a well-known theorem. So it provides a format or codebook method for solving recurrences in the form Tn, running time of an algorithm with respect to n. N is the input size equal to a times t of n by b plus fn. This fn is another function. Okay, so that is, this function is that it denotes the time that is needed to divide and conquer process. So we know that master theorem it used for divide and conquer process, and a and b will be some positive numbers. It's greater than the constant. For instance, a greater or equal to 1, b greater than 1, and fn is an asymptotically positive function. Asymptotically positive means if we go like, if we draw a line This is geometric line, right? So this is x-axis and this is y-axis. So we know that this x positive value and y positive value. This quadrant, this first quadrant is called positive. X goes positive and y goes positive. And this section, this part, it goes negative. X goes negative, y goes positive. And these sections is x goes positive value and y gets negative value. And this section, this quadrant, or this, we say x negative and y negative. Okay, so we know that the first quadrant is positive for x and y value positive. So a function, if it goes this way or this way or even that way, we don't know yet. So asymptotically positive means it never will cross this boundary. Is this y axis, is this never will go negative side of, this is the boundary, right? Y axis is the boundary for x value and x axis is the boundary for y value. It will pass this y axis and never this will pass. Okay, this is means asymptotically positive. Asymptotically positive function. Okay. So in asymptotic, in far location, in infinite location, still it will be in first quadrant. Okay. So in order to solve, to use master theorem to solve any recurrence problem using master theorem, we need to understand three cases. There are three cases for master theorem. If you understand that these three cases, hopefully you will be able to use master theorem for solving many recurrence problem. I said many, but not all. We will see the limitation of master theorem. So there are some cases that we cannot use. Okay. So there are three cases here. Okay. So there are three cases of master theorem here. So when you these three cases. So first of all, let's recall again the master theorem again. So let A greater than, so this is the master theorem in mathematical format, it says otherwise. If A, let A greater or equal to 1 and B greater than 1 with the constant A and B constant number, and if Fn is a function, okay, then Tn can be defined on the non-negative integers and non-negative integers by the recurrence. Non-negative integers, that means asymptotically positive. Previously we saw. This is the formula master theorem. Okay. So here one thing is that, as we discussed, that here n by b, that means either it takes floor or it takes ceiling. N by b cannot be always an integer number. In case it is not integer, because n, if n is not an even number, then n by b, okay, okay, the n by b will not be an integral number. In that case, if we take ceiling or floor, then we will get an even number, an integer number. So in both cases, so by this notation t of n by b, we can mean floor or ceiling. Okay. And these are the three cases for master theorem. Number one, Okay, so if fn, so what is fn about here? Fn is another function. Okay, fn is a function. This fn, if this fn, okay, equal to, can be written as big O n to the power log ba. So log ba, in mathematics it says log is base 10, but in computing we will say lg, that means with base 2. Okay, so if fn equal to big O, look at this carefully, big O n to the power log ba minus epsilon. So epsilon is a positive some constant. It can be a whole number or it can be a fractional number, decimal number. Then we'll see that Tn, the running time, equal to Tn equal to theta of n log a ba. This theta of this one. Of this part, we will just get rid of the epsilon part. Okay, we will come up with some concrete examples. Okay, and the second one, it says if fn, this fn equal to exactly here is of n to the power log ba, then fn equal to, we multiply this value by log n times log n. Okay, and here you see that what is the value of our epsilon over here? Is epsilon equal to 0 over here, right? That a, that means is epsilon equal to 0 over here, and here epsilon not equal to 0, and here actually you can say epsilon equal to 0, something. And the third condition, third case, is that fn equal to, is a lower bound omega n log n to the power log b plus epsilon. Okay, for some constant epsilon, and it has some extra conditions as well, as we'll come this extra assumption later. Okay, and then Tn equal to theta of fn. So what is fn? We will have fn given. Okay, but the first two cases, you see that, okay, there is no fn here or here. There is no fn. We will get the different value over here. But in the third case, we will have running time equal to theta of fn. Okay, now we will go through these three cases one by one with some examples. Okay, now at this point, has anyone any question? Okay, please speak out. But this theorem is a little bit critical and confusing. So my goal today will be, if I can help you to understand this master theorem, then I will be happy. Has anyone any question? Let me get the attendance. Okay. Okay, assignment is not posted yet. I will post assignment this weekend, and the assignment will be due. First assignment will be due next weekend, right? So the assignment will be due next weekend. So I have not posted it yet. I'll post it by this weekend. So then you will get a whole week. So then, so that our assignment 1 will be based on asymptotic notation and master theorem. And okay, so today we will complete this and then we will get an assignment. Okay. So no, actually, as assignment 1 will not be any programming task. It will be some definition. You have to write some definition like big O, small O, omega, theta notations, and then you will given some. You will be given some problems, and you have to explain that we solve that problem in master theorem. No, the assignment will not be exactly. This is summer assignments. There will be something different, but there may be something similarity. Don't. You can look at my assignment from the summer semester, but that will not be exactly one. Okay. So now whatever we are discussing, let us go through this. So in that case, let us see that what we have so far discussed. In all three cases, what we are discussing, what we are comparing this one in log BA with FN, right? We are comparing this part in log BA with FN, right? So then we need to understand that. For instance, let us see that what this say. So you need to read this carefully. Okay. So before applying the master theorem to some examples, let us spend some moment trying to understand what it says. In each of the three cases, we compare the function fn with the function n to the power log BA. So intuitively, what we are having here, the larger of these two, the larger of the fn and n to the power log BA determines the solution of the recurrence. Okay, so in that case, if fn equal to, for case 1, fn equal to big O n to the power log BA minus epsilon with some positive value. If we, then which one is larger? This part is larger, right? So because we are subtracting this epsilon, subtracting some value, positive value, to make this equal to this. Unless we subtract this epsilon, this part is larger. This part is larger, right? So in that case, our Tn value is the larger one. This is the larger. Tn value is larger one. Okay. And in the second case, if they are equal, that means epsilon equal to 0. Yeah, right. It's epsilon equal to 0 over here. Then we have this, that the running time will be this with multiplied by some logarithm values. Okay, and in the third case, which one is the function larger? Is fn is f of n is larger, right? So because from epsilon, this one epsilon of sub omega of n to the power log ba plus epsilon. We are adding up something with a to make it is equal to this. That means in that case, which part is larger? Fn is larger, right? So then Tn equal to Fn. So in all cases, actually the two cases, 1 and 3, we are having the result, okay, the running time with a larger value between these two values, between Fn and log and Fn and n to the power log Ba. Whatever is larger, we are having that as our result. Okay, has anyone any question? Is it understandable? Do you understand this? Now we will come up with some some examples. So in the second case, this one is Fn, right? If equal to this one equal to this one, and theta equal to Fn of log n. Okay, beyond this intuition, there are some technicalities that we need to keep in mind. In the first case, not only must Fn be smaller than n to the power log Bn, it must polynomically smaller. Polynomically smaller means that we call otherwise it's asymptotically smaller. In any case, it cannot be larger. Okay, that is Fn a must be asymptotically smaller than n to the power Bna by the factor of n to the power epsilon. Okay. For some constant value of epsilon. So by the factor, that means multiplied by the factor n to the power epsilon. We know that if we multiply this, okay, this by this, then we will get the power in this plus n. This into the power this plus epsilon. Something like this, something like this. Okay. In the third case, not only the Fn be larger than this, it must be polynomically larger. Okay, so this is the in addition, and there is an additional condition over here. This we will come back here soon. Okay. So note that in all three cases, we do not cover all possibilities for Fn. So there is a gap between 1 and 2 and 2 and 3. Okay, so there's the gap between 1 and 2 when Fn is smaller than this one, but not polynomically smaller, not asymptotically smaller. Similarly, there is a gap between 2 and 3 that Fn is larger than this, but not polynomically larger. If the function fn falls into one of these gaps, these are the two gaps that the master theorem cannot be applied. So if fn falls into one of these gaps, or if it is if the regularity condition in case 3 fails to hold, then we cannot use the master theorem to solve the recurrence. So in shortcut, we can say that we cannot apply master theorem for all cases. Okay, let us see some examples. So these are some examples that using master theorem we will solve this this problem. Okay, we will solve. So this is our problem in hand. We are given a function Tn equal to 9 times T of n by 3 plus n. So here, let us do that. So considering this one, what is a value? A equal to 9, right? And b equal to 3, right? And fn equal to n. Fn equal to n. So we are given this formula, right? So now we need to calculate n to the power log ba, log f